everyone, today we are looking at notes 5-8, the discriminant, but before we get to the handout, you actually need to grab some notebook paper real quick, and there's some definitions I need you to write. So here are your definitions that we're going to talk about in these notes over discriminant. So there are all different types of numbers, okay? This year, we have dealt with real numbers, both rational and irrational. We have dealt with complex numbers, and we have dealt with imaginary numbers. So let's talk about the definition of each. So real numbers include the rational and irrational numbers, not imaginary numbers. So a real number does not have any imaginary part. Okay, a rational number is any number that can be expressed as a fraction, p over q, where p and q are integers or whole numbers. Some examples of rational numbers are 2, -5, 4/5, -1/3, because we can write all of these as a whole number over a whole number. -5 could be -5 over 1, 2 could be 2 over 1. 0.25 can be rewritten as 1/4, so on and so forth, okay? 0.6 repeating, remember that little line up there means repeating, is the same thing as 2/3. So all of these decimals can be rewritten as a fraction, okay? An irrational number, however, is any number that cannot be expressed as a fraction. When written as a decimal number, okay, they do not terminate, nor do they repeat. Terminate means end. They do not terminate, and nor do they repeat. So this doesn't terminate, but it does repeat. Okay, so an irrational number when written as a decimal does not terminate and does not repeat. Some examples of irrational numbers is pi. You know, pi goes on forever and it never repeats. E, okay, square root of 5, square root of 7, any square root that doesn't simplify further to where you can take everything out of the radical, that's going to be an irrational number. So what's a complex number? A complex number is a combination of a real and imaginary number written in the form a plus bi, where a is the real part and bi is the imaginary part. So like 2 minus 3i and -7 plus 6i. In fact, a complex number could also be just an imaginary number. This could be a complex number if there was no -7. And they would say that the real part is 0. Okay, so it'd be like 0 plus 6i if the -7 wasn't there. Okay, and also actually a real number, like say if this was just -7 without the plus 6i, that would also be considered a complex number. They say that is a complex number. It's just that the imaginary part is plus 0i. Okay, so technically here, this should go numbers to complex, and then from complex you should have imaginary stemming off of that and real stemming off of that, because a complex number can be just imaginary, or a complex number could be just real, or third, a complex number could be a combination of both together like these. Okay, but we're not getting too much into that today. All right, so here's where we're really focusing today, okay? I needed you to know these definitions so we can use them today for our lesson. So we have been working with quadratics for quite some time now, and more recently what we have been doing with quadratics is solving them, finding the solutions, roots, zeros, x-intercepts. Okay, we have learned lots of different ways to solve a quadratic, and one way we're going to learn here soon is the quadratic formula. So you have used quadratic formula before in Algebra 1. Okay, and this is I won't say easy, I'll say straightforward, and what's nice about it is it works every single time. Just a straightforward way to find the solution, zeros, roots, x-intercepts of a quadratic, okay? So the quadratic formula goes x equals, or the solution, 0, root, or x-intercept equals, opposite of b plus or minus the square root of the quantity b squared minus 4ac all over 2a. So what we're talking about today is this little part under the radical, the b squared minus 4ac. That's called your discriminant. Okay, so not the radical included, just what's under the radical. So the discriminant is just b squared minus 4ac. Okay, and depending upon what kind of number the discriminant is, that will tell you how many and what types of solutions your quadratic will have. So if your discriminant is a positive perfect square, if this number, if you compute this number and it ends up being a positive perfect square, like think of examples of perfect squares, 16, 81, 4, 49. So if the number is a positive perfect square, the quadratic will have two real, not complex, okay, not really, not imaginary, two real rational solutions. Okay, rational because you can take the square root of a perfect square, and this discriminant is under the radical. So when you take the square root of a perfect square, it ends up coming out of the radical, right? That should kind of make sense to you. However, when you have a discriminant that is a positive non-perfect square, like 11, like 7, okay, then you're still going to have 2, and they're still going to be real because we're talking positive here. And now it's going to be irrational because, y'all, I want you to think about this. Okay, remember your irrational numbers were numbers like this in a radical sometimes. Okay, so if your number here, if your discriminant is not a perfect square, if what's under the radical is not a perfect square, then you're going to have some numbers remaining under the radical. Therefore, you will have an irrational answer. Yes? Okay, if your discriminant is negative, think about it, y'all. If you have a negative under the radical, what does that mean? That means imaginary, right? That's going to mean an I comes out. But we won't just call it imaginary because you'll have this part that's going to be a real part and this part that's going to be a real part. There's not going to be any I here and there's not going to be any I here. The I is only going to come from right here. So you're going to have two complex solutions is what we say, because it will combine both an imaginary part and a real part. Okay, so two complex solutions. All right, and when your discriminant is 0, think about it, y'all. What's the square root of 0? It's 0. So if you have a number here plus or minus 0, what's 4 plus 0? Oh, it's 4. What's 4 minus 0? Oh, it's still 4. So we call this, there's going to be one real solution, and we call it a double because you will get the same solution twice. And I promise this stuff might seem a little weird right now, but when we start working with the quadratic formula, you'll be like, oh, okay, yeah, that makes sense. So for now, I just really need you to memorize this. Yes, I said memorize. This will be on the test and you won't be able to use this chart. But for now, memorize this, and then we will really explore it when we do more quadratic formula in the coming days. Okay, so how will the graph look when you have two real rational solutions? Well, the graph would look like maybe something like this, where the graph crosses through these two integer values. Okay, maybe something like that, or maybe something like this, where the graph is upside down. Okay, and we cross through two integer values. That would be your two rational solutions. Our two irrational solutions would be something like, oh, well, here's your integer values, and then it crosses through here and here, and they're not like fractional, like that's not 1 1/2. It's not a pretty value, okay? It's a crazy, weird value. So something like that, or even could look upside down, something like that. How does it look when you have two complex solutions? Oh, I hope you know the answer to this one. When you have an I in your answer, it'll look something like this, where it'll never cross. Or maybe something like this, where we'll never cross the x-axis. Sure, I'll cross the y-axis, but I'll never cross the x-axis. How does a one real double look? You know, you've seen it before. It could look like this, or it could look like this, and say it's got to be on a, let's see, something like that. Okay, but again, this is a one real double, oops, and I should say one real rational double, because it is rational. That's what I was getting at. One real rational, it's a double. Okay, because 0 is a perfect square, right? So it will be a rational answer. One real rational double. Okay, and it could land on a half, okay, or something like a third, but it couldn't land on something ugly like 0.425683, something that repeats and goes on, or never repeats and goes on forever. Okay, so let's practice what we just learned. All right, find the discriminant and state the number and types of solutions. Okay, so in order to find the discriminant, we need to know what B, A, and C are. So this quadratic has got to go into standard form. Okay, so that means in this case, easiest thing to do, since we've got two terms here on the left and one term on the right, easiest thing to do is just to move this one on the right over to the left, and specifically it needs to go in the middle. Okay, so we'd have 4x squared minus 4x plus 1 equals 0. Now we're in standard form, and we can say that A equals 4, B equals -4, and C equals 1. Right, so I'm going to kind of give myself some space to work over here. So I want B squared minus 4AC. Okay, so B squared, I could write it like -4 squared minus 4 times A times C. So that's 16 minus, I always drag down the minus and then ignore it. And then 4 times 4 is 16 times 1. So that's 16. So 16 minus 16 is 0. So my discriminant is 0. And I'm going to put a semicolon there. And what does that mean? That means if my discriminant is 0, it means one real rational, and it's a double. One real rational and a double. So if I were to graph this graph here, if I was to plug it in the y equals of the calculator or get it into vertex form myself and graph this, I would find that it would look maybe something like this, to where the vertex lies on the x-axis and either faces up or down. Well, we know based on the a value that it's going to open up. Okay, and then we're just going to have one real rational solution. Okay, so now let's work on this guy. So similar, we need to get that 10, but it goes in the back. So x squared plus 2x minus 10 equals 0. So A is 1. I'm going to kind of draw a line here too. A is 1, B is 2, C is -10. Okay, so that puts me with B squared minus 4AC. So 2 squared minus 4 times A times C. Okay, so 4 minus, and then 4 times 1 times -10. So 4, remember the minus already dragged down, so we're not talking -4 times that. We just drag the minus down. Okay, so 4 times 1 is 4, times -10 would be -40, so minus -40. So that becomes a plus, so that's 44. Okay, so what does that tell us? Okay, that's a positive. Is 44 a perfect square or a non-perfect square? Oh, it's a non-perfect square, so that's 2 real irrational. So again, if we were to find the solutions of this quadratic on number 2, then we would see that our two solutions would be real numbers and they would be irrational. So no I in them, and they would be irrational. Okay, so let's keep going, just a couple more. So let's really get this one in order. So the -x squared stays -x squared. It didn't jump over the equal sign, so the sign stays the same. The 2x stays the same, but we're just putting it in the correct order. Now the 4 does jump over the equal sign, so it becomes negative. So therefore, A is -1, B is 2, and C is -4. Okay, so B squared minus 4AC is going to give me 2 squared minus 4 times -1 times -4. Okay, so this is 4 minus, and then I cover that. 4 times -1 is -4. -4 times -4 is positive 16. So I just write 16, so that's -12. Okay, that's a negative number, so that means 2 complex solutions. 2 complex. Okay, so here we've got 4x squared minus 16x plus 7 equals 0. So A equals 4, B equals -16, and C equals 7. I better bust out my calculator for this one. Let's see. Let's see how bad it gets. Okay, B squared minus 4AC C. Okay, so we've got negative 16 squared minus 4 times A times C. Okay, so I know this is 256 minus, and then 16 times 7 is 112. Okay, so 256 minus 112 is 144. So 144, that's positive, and it's a perfect square. So 2 real rational. 2 real rational. I think y'all are probably getting the point. Okay, but I've got 2 more here. So make sure you put this in the right order. 2x squared minus 2x plus 5 equals 0. So A equals 2, B equals negative 2, and C equals 5. So B squared minus 4AC. So negative 2 squared minus 4AC. So 4 minus, I can already tell this is going to be complex. Okay, that's 8 times 5 is 40. So this is negative 36. So remember, I'm negative, okay, and it doesn't break it up into perfect square or non-perfect square. So it doesn't matter that this is a perfect square and that wasn't a perfect square. If it's negative, the only thing you say is too complex. Okay, we're almost done, y'all. Thanks for bearing with me. So 2x squared minus 3x minus 8, so equals 0, sorry, and A equals 2, B equals negative 3, C equals negative 8. So B squared, oh no, my pen wants to give out. No. Okay, negative 3 squared minus 4 times A times C, so 9 minus 4 times 2 is 8. And then 8 times negative 8 would be negative 64. So that turns to plus. So 9 plus 64 is 73. And that's positive and positive and not a perfect square. So this is going to be 2. Oops. It's supposed to be in red. 2 real irrational. That's it.